is currently working as a professor in Mechanical Engineering Department of Nirma University, Ahmedabad. He has done his BE in Mechanical Engineering and ME in Thermal Science from MS University of Baroda and PhD in the area of heat transfer from IIT Roorkee. He has over 20 years of academic experience and has published over 20 papers in international journals and conferences. He is associated with the Thermal Insulation Laboratory at the Nirma University, Ahmedabad, set up under the AICTE NAFETIC scheme and also member of BIS Technical Committee on Thermal Insulation. We are very lucky to have you, sir. I request you to please start your session.
Thank you, Professor Ragesh. Am I audible?
Yes, sir.
Yeah. Okay. So very good afternoon to all. I am happy to be here and delivering this session with you and sharing some of my experiences of working with thermal insulation as a means of energy management. Here, can you see my screen? Is my screen visible?
Sir, it shows a blank screen.
Okay.
Yes, sir. Now it is visible.
It's visible, no?
But it is not showing in full screen. It is showing in a small screen.
Okay. Yes, now it's okay.
Yes.
Okay. So thank you. Thank you very much, Professor Ragesh, and I thank Dr. N.M. Bhatt sir for this opportunity on this session today. The topic is effective thermal insulations for efficient energy management. So here some of the topics which we will be looking forward in today's session include what exactly how thermal insulations actually work and how they are relevant in the process, how the high temperature and low temperature applications may have different requirements of thermal insulations, and what are the desirable properties of thermal insulations. So with this, we will just have an overview because it's a very vast topic in itself. But in a session, we can definitely appreciate how they can be efficiently applied because many times we apply, but we are not careful. And also some of the properties which we need in an insulation, we may, if we overlook it, then definitely will not get the perfect results. So this is something like what we all know, that is known as the Fourier's law of heat conduction. So usually whenever you have a wall and you want to reduce the heat which is being moved, what you need to do is you want to play with this thermal conductivity, because the cross section area is what you have. This is a wall, you cannot do much about it, and the temperatures of the ambient and the fluid, they are also sometimes beyond your control. So what you can practically do is play with the thermal conductivity. So if you have, if you see this equation, so in this equation you can just write it as Q is equal to delta T upon, so you have delta X here. So if you see delta T is the gradient which is actually working here. So if you see the delta X upon Ka, so this part is your thermal resistance. So if you can do so, this is something which you like to have. You can say if you are working as an insulator, you would like to have this higher side so that the heat you would like to play the role. So insulations basically are doing like this. So the thermal conductivity you are reducing as much as possible so that the resistance part increases and the heat transfer reduces. So we all know that the gases, they have the lowest thermal conductivity, and air is something which is freely available and its conductivity is around 0.026 at the room temperature. So this is the thermal conductivity of air. So if air, most of the insulation material, they actually make a good use of air pockets. So if you see some of the insulations which we usually use like foams. So foam is your very popular insulation material, or PUF, what is known as polyurethane foam. So in the refrigerator doors and all, we usually go for the foams. and they have a structure which is basically what you do is you fill some gases like some refrigerant as a foaming agent. So again, gases are very low conductivity and they are filled in this plastic, you can say the base is the plastic spheres in which the pocket you have the refrigerant as the gas filled. So because of this, the foams have very low value of K. So this is essentially what you are using is the air. On the higher side, when you go for materials like wood, water, so the conductivity increases. At the same time, when you are using these foams, you have to see that there is no open structure. So if the structure of the foam is open, like if it is something like this, and the cells which you are forming the foam is not perfectly closed, then the water can get into this. And water's conductivity will be in the range of 0.5 or so. So it will be, so from 0.02, you are simply increasing it to that order. So this is where the in the application of the insulations, you have to see that water does not get into the systems. This is what we were just talking about. So you have diamond, which is the highest, and you have water around here, which is around 0.6, and you have air, which is around 0.02. So your foams, which have basically a conductivity of 0.026, they principally are due to the presence of the air or the pores wherein the air or some other kind of gases are there. And this is what leads to the low conductivity of the material. But again, as I told you, if the structures are open, then you can have water getting into it, and that water will actually increase the conductivity of the material. So we all know that there are three modes. So heat can within the material, if you see, there can be all the three modes could be working at a time. So depending on the way the fluids are placed there and how the structure is. So even the radiation sometimes can play a role. So here, if you see the structure of an insulation, so if you take a fibrous insulation, so if you take like a glass wool, you must have seen the glass wool or say mineral wool. So in this, these are all the fibers. Okay, so it is basically a kind of a blanket. So in between the fibers, you have these gaps. So here there will be a combination of heat which will be flowing due to the, so the wall to wall, there will be heat conduction. Again, some amount of conduction and convection through the air which is in between. And then so heat propagates like this. So actually in any heat transfer which is happening in an insulation wall, you have a combination of the convection, radiation and conduction. And your objective overall is to reduce all the three modes through this cross section. So this is for a fiber mass insulation like a glass wool blanket or a mineral wool. And this is something which you go for a cellular like puff, polyurethane foam. So foam structure is something like this. So these are the cells which are actually formed by the, you can see the chemical structure of the puff, which is kind of a polyurethane structure. And within it, you have some kind of a gas which is filled in between. So you can use as a refrigerant, as a foaming agent, and that is what is filled in this kind of a structure. So if these pores get opened up, again, you have the problems of maybe some water which can get into these structures. So if it is a close-knit structure where there is less number of open cells, the structure is very compact and it will not be prone to heat transfer as compared to a open type of structure. So insulation materials, basically you can have inorganic material. So inorganic, you have something like perlite, you have the ceramic fibers, mineral wool, cellular glass, and so these are all the inorganic materials. Then you can also have the organic materials. In organic, you can have natural and you can have man-made. So in the organic, you have this foams, which I was just talking about. So like polyurethane foam. Then there is PIR foam, isocyanurate foam, and there is something like which we usually use on our human body, like you have the sheep's wool. So that is a natural organic insulation. Okay. Then you also use cotton. So these are all the organic materials which are used there. Here, if you talk of the properties, one of the most important property is the thermal conductivity. So here we use the word effective. We use the word effective because it is not only the thermal conductivity of the material, solid material. It is also because, as I told you, in this structure, the overall heat which will be moving is a combination of the heat which is being transferred through the fibers as well as the air and other gases which might be in between. So it is not just the conductivity of the material per se, but it is also due to the combination of the paths which are formed, and the overall thermal conductivity is also what is known as the effective thermal conductivity. So it is not just the thermal conductivity of the solid material, but the whole insulation wall, which comprises of not only the solid fibers, but also the gaseous elements. So we use the proper word in case of thermal insulation as effective thermal conductivity. So here you will find most of the plots are with respect to the effective thermal conductivity. So as we all know that thermal conductivity of the material is a property. So K is also going to be dependent on the temperature. So the temperature of applications. So if you see, most of the time as the temperature is increasing, the thermal conductivity of the material is also increasing. These are all insulation materials, and most of them exhibit this kind of behavior, that as the application temperature increases, their conductivity also increases. But as you can see, it's not very steep as such. Suppose you take this material, so at around 2 or 300 or so, it is around 0.2. Whereas if you go for say 600, it becomes 0.25. So there is some change from 0.2 to 0.25. So which is for almost you can say 300-degree rise. It is not that much. But anyway, we have to appreciate that the as with the application, the conductivity will also change. So insulation may not just have one purpose. Thermal insulation, you may have the purpose of say heat reduction. So you can use it in the, it may be both ways. Okay, it can be for cold insulation and it can also be for hot insulation. So this both applications may be differing. In industry, you may find some of the cryogenic systems where you require cold insulations, and you may also have the streamlines and the you can say the steam going to the high pressure turbine. So all those are the hot insulation where you require to maintain the temperature of the fluid inside the pipes. So this is again you can have different type of applications. So thermal insulation may be used for that. Also another application of the insulation is in acoustics. Say for example the airports, okay, or the theaters. So there you may use the acoustic insulation. Okay, for example near the airport. So if you are inside the airport, you may not feel the kind of noise which actually the airplane makes on the airfield outside. There are so many airplanes are landing and taking off, but still within the airport premises you don't feel it because of the insulation which is used. And this noise level control is also done by insulation, and that is known as the acoustic insulation. Usually rock wool is a very good acoustic insulator. Then the third is which is very actively used but often missed is called the fire protection. So here say in some of the plants, suppose for example this is storing some kind of a very hazardous and you can say combustible, say for example of a fluid inside this tank, and suppose there is a sudden rise in temperature, then what will happen is this structure will have an explosion. It can have it because of the high temperatures. So the insulations which are put over the wall, they have to be very effective. So this is also yet another safety aspects of the fire protection. Another thing is when you are using in buildings, buildings again you are using in buildings for energy management, because if you are using it efficiently, you can cause a lot of reduction in the amount of heat transfer which is happening, and so your air conditioning load and the thermal management of the building is very effectively done if you are using it. But at the same time, you have to see that the insulations you are using are fireproof. There have been incidents wherein people have been careless about the fire property of insulation, and this has caused very drastic losses to the human life. Okay, so this is also one part. So as I was telling you, you can go for thermal insulation. So usually hot insulation is above ambient, and you can go up to 700 plus temperatures. And you can, if it is cold and cryogenic, you can go for below ambient and up to minus 200. So this is typical ranges, but of course these are only indicative ranges. So fire protection, I was just telling you that in case of the event of a fire, your vessels, structure, supports, they should be designed for at least 2 hours fire protection so that their critical temperature is not reached. Otherwise, what can happen is before the firefighters come, the structure should never, kind of reach the critical points. Otherwise, there can be disastrous results. So insulation is very effective in that kind of passive fire protection. So what is important is property aspects of insulation material, what water can do, and water, as I told you, its conductivity is much higher, maybe more than 200, 300 times that of air. So it will cause very disastrous results if it gets into the system. So you have to see that water is not getting in the system. So like I was telling you, air conductivity is around 0.026 and your water is around 0.6. So between the two, you have a factor of around 30 times. Okay. So this is something you have to see, that if you have designing system just with the air pockets of the you can say the cellular structure, if the water gets into those structures, it can lead to a lot of heat transfer. So your entire thermal management will fail. Then you have special characteristics for hot insulation and cold insulation. The another important aspect which people often miss is the corrosion aspects. So the corrosion aspects are important because usually once you have placed the insulation, you will not open it in the lifetime of the insulation. Maybe you will open it after 5 years, 10 years, when the insulation has become old and you want to replace it. At that time, you might find that if the certain properties like corrosion under insulation, that is known as CUI. Okay, so this is something which is very risky, and this can lead to the corrosion of the wall. So typically the austenitic steel, if it is there, and the amount of chlorine in the insulation or the sulfur content is not appropriate, then it can cause the insulation, can cause the wall, especially like the metallic walls, to corrode. And this is something also which comes into the issue, because this is something you will not know unless you open the insulation, and once you have put the insulation, you will not usually open it periodically. Okay, even for cleaning or other things, it is just put in place, and unless the insulation is bad and it has collapsed, we do not usually replace it. But because it is hidden, it can silently cause corrosion. Then acoustic insulation we just talked about, and the fire protection. So this is something which we have to look into the aspects connected with the insulation when you are putting it for the thermal management. So here the design objectives which you say, one is the energy conservation, that is the prime thing, and the logic is simple. If you have a pipe, and over the pipe you have put the insulating wall, so here you are creating additional resistance. So the value of overall heat transfer coefficient U will be affected because of the presence of the wall. So, but at the same time, you have to see that Q is equal to U into A into delta T. So if you are using a thick layer of insulation for a pipe, the area is also increasing. Okay, so if you are having a very effective insulation, ultimately, if you are having an insulation which is where the wall, suppose instead of using this insulation type 1 is having say 10 centimeter wall thickness. So delta D is 10 centimeter. So this thickness is say 10 centimeter. So what you have done, actually your outer area is increased because of this. And here suppose you are using for the same wall temperature, you are able to maintain delta T same for using only say 2 centimeter wall. So if your thickness here is just 2 centimeter, what will happen is this area will be much larger as compared to this area. So even though wall temperatures outside and of the two surfaces is same, but for the pipe, this material which is say type 2, but only requiring 2 centimeter, it is able to create the same thermal resistance as a 10 centimeter because of this having a very low thermal conductivity. So this, as compared to this, the wall thermal conductivity is higher, though it is an insulation. So the smaller thickness of this wall will lead to a lower value of Q. So even though walls are at the same temperature, both are at say temperature Ts, but because the area here will be lower, so you will be able to have lower heat transfer to the atmosphere. So here the energy conservation is also linked how is the conductivity of the material. So thermal conductivity of the material is something which is very relevant when you are selecting the material for an insulation. Then the personal protection, because sometimes the wall temperatures you are maintaining. Suppose you are maintaining the wall, there is a steam line here, and say it is carrying 200 degrees Celsius temperature, and the outer surface temperature you are maintaining is say 50 degree. So it is safe because the personnel who are working around, they may touch the lines and they are not getting affected. Okay, it is both ways. It can be also there for cold lines. Suppose you are having a cryogenic fluid here, and with the insulation, the surface temperature is maintained. Say instead of having minus side, suppose here you have minus say, or you can say 77 Kelvin inside, and outside temperature, suppose you are able to maintain at say 300 Kelvin. So if the wall is touched by humans, they are safe. Both ways they are safe. So the personal protection is also one of the objectives which you do. So energy conservation is definitely one, personal protection. Then the amount of condensation you want to control. So if you're not able to maintain the temperatures, then the condensation can happen in some of the processes. So you can, with the use of effective thermal insulations, you can control the amount of condensation which is happening. The processes may be very strictly maintained by the temperatures regulation. So you may require to maintain the temperatures within a small band. Say if your process is going on and it is required that its temperature should not exceed or it should not lower a certain range, then that can be very effectively done using the insulation. So then the freeze protection. So it is something which is, some of the things will freeze if you are not maintaining the temperatures. So this is something you can again use from the insulation. Then the noise and the fire safety, which we just talked about. So here, what are the important parameters of an insulation material? One is the maximum operating temperature to which an insulation can be used. Then the thermal conductivity of the material, thermal transmittance. Thermal conductivity and transmittance, though they are linked, but they are not the same because here you also consider the say you are considering the overall factor. So U, when you are taking U into account, so you talk of the thermal transmittance. Otherwise, it is you're only taking K here. So as you know that the overall coefficient depends not only on K, but it also depends on H. That is the convection coefficients. So you require to consider that. Then the water vapor permeability, how much the insulation is permeable to the water vapor. So usually what happens is that the water's vapor will have a gradient here. Say if you are taking off a cold storage, for example, in a cold storage, this can be a very severe issue. Suppose you have on one side of the cold storage, you have say you are maintaining a temperature of minus 20 degree. Okay, and on outside ambient, you may have a temperature of say 25 degree. So this is ambient and this is cold storage. So the water vapor on this side is at a different gradient as compared to this. So again, there will be a movement of the water vapor from the plus side to the minus side. So how much the wall is permeable to the water vapor? This is a very relevant property, especially for cold storage. So what will happen is, if water penetrates the wall of the cold storage, then the water's conductivity is say 0.6. Okay, and you have designed the whole wall considering the insulation to be effective insulation. So your load for the cold storage is designed as per that. But what has happened is now water has entered. Now because water has entered, so what water will do, it will replace the air pockets inside, and these air pockets were earlier having a conductivity of 0.02. Now the water has replaced it, and it is now the wall has become conducting. So ultimately, because it is a cold storage, this water converts to ice. Eventually, water will also convert to ice. So it will expand, and ice conductivity is around 2. So right from from 0.02 you move to 0.6 and then to 2. So ultimately your wall becomes highly conducting. At the same time, the volume of the ice will be larger, so it will create a pressure on the walls and it can damage the walls. So your cold storage, so water vapor permeability is a very important property, especially for the cold insulations. How much absorption of water take place? So absorption of water is again, as you can understand. Fire resistance, we just talked about it. Smoke properties are also important, because when an insulation suppose catches fire and it burns very toxic smoke, then that toxicity, especially in the residential and this kind of buildings, it can have a very serious repercussions. Then the compressive strength, because usually in the cold storage and other structures, you will have a whole wall which is created of the insulation material. So these walls will have a load. So this load will be of compressive nature. So if the insulation is not very strong, then its compression properties will not be sufficient. So you should know how much compressive strength it should have. So it is good to have a good compressive strength, especially when you are using it for buildings where the loads will be coming into it. Resistance to vibration and jolting, this becomes crucial, especially in automobiles and those kind of structures. Say for example, you are using in trains. Okay, in trains, trains are continuously vibrating. So the railway bogie, okay, the air conditioning coach is there. So usually to reduce the air conditioning load, you will use the insulation in the walls. So the whole wall of the coach will have insulation in between. So there will be insulation here. Now this is continuously vibrating, okay, because the train isn't moving, so it will always be vibrating. So what will happen is, suppose you have used a blanket, okay. So blanket, say it is of glass wool. So glass wool's blanket is put here. Now this train is going to move, this coach is going to move 24/7, 365 days. It is continuously moving. And so this blanket, it is possible that it may have some kind of a settlement. So instead of this, it is something like this is created. Okay, so it is a wall may have a kind of a vacuum structure building up in between. So how it is resisting the vibration and jolting becomes relevant in case of structures like train and all that. So in the coaches, especially you require to have this. Corrosion behavior I just talked about, and chemical resistance. So some of the properties, chemical properties should be such that it is having a kind of a neutral behavior and it does not degrade chemically with respect to time. Radiative properties become more relevant in case of insulations which you use in the radiation applications. For example, the reflective surfaces should have very high reflectivity in the long run. So if a material is having a good you can say the reflectivity. Usually we know that when we want to reduce the radiation heat transfer from the surface, we go for a highly reflective surface. And the surfaces which are used for the application of radiation. So if you have the concept of the radiation shield, so it basically works on reducing the surface resistances. Okay, so or sorry, you will increase the surface resistances. So what you go is for the emissivity of the material should be low. So you all know that the total sum of the emissivity or absorptivity plus reflectivity will be equal to 1. So for any opaque surface, so if a surface is opaque, you have this true. So that means because your emissivity is also equal to your absorbivity. So this is equal to 1. So usually if you want to reduce the emissivity of the surface, so then you need to increase the reflectivity. So the total of the two will be equal to 1. So your reflectivity should be large. So most of the time you use materials which are highly reflective for reducing the amount of radiation which is going to be encountered. So this is how the radiation properties become more relevant, and you go for reflecting surfaces whenever you want to reduce the heat which is being transferred from the surface. So if you talk of the various properties of the material, so you have the thermal properties, physical properties, chemical properties, then the moisture properties, combustibility properties. So these are something which are very relevant, and you need to start and you need to appreciate this. Again, it will also depend with the application. So for different type of applications, you may require different type of properties. You see, water absorption may not be very critical for high temperature application. Why? Because even if water gets into the system, if you have, because you are having inside the say wall, you are having a high temperature fluid. So water will eventually evaporate out. So this is something which is very crucial for the cold insulation. How much water vapor gets into, how much water it is absorbing, it is very crucial for the low temperature insulation, because once water gets into, it will not be able to come out, and it will freeze and it will become ice and it will start highly conducting. But in the case of high temperature application, if the water gets into and the say temperature of the fluid inside is 150°, water will eventually evaporate and it will come out. So only you have to see that there are enough path lines available for water to come out. So likewise, other properties are also very relevant, and depending on the application you have to do. So your temperature properties include your temperature limits, thermal conductivity, how much it expands. That is also important, because if you are putting it on the pipe's differential expansion and the expansion of the thermal insulation you have put, they are also very relevant. Thermal shock resistance, thermal diffusivity. So how fast it is able to come down to its original temperature, and how fast it wants to cool down, so that is thermal related to the property called thermal diffusivity. Then the emissivity of the surface, again it is something related to the reflectivity and the specific heat. So these are some of the thermal properties we look for. Similarly, if you talk of the physical properties, it is how many open and closed cell structure is there. We just talked about the open and closed cell. So it is relevant because that is how the path lines are decided inside the insulation. Then whether it is fibrous or it is rigid, it is resilient, it is resistance to vibration, tensile strength, flexural strength, compressive strength. Flexural strength is something related to the breaking. Suppose you are having a sample like this, and you are having a load in the center, for example, and it is like a structure like this. So at what load? So it will usually have a sagging. So when you load it like this, so it is under flexion. So here at what load this will bend and it will break. So that is known as the flexural strength. So in some of the cases, depending on the way you apply the insulation, this may also be relevant along with the compression. Then chemical resistance included what is the pH value, leachable chloride, because that is what leads to the corrosion. Okay. Then moisture properties, how much water vapor it is transmitting, what is the water repellency, water absorption, and the hygroscopicity. So how much it is able to absorb the moisture from the air. So all these things, determine the moisture properties of the insulation. As such, we all know that water is not desirable as such. Then flame spread index. So in the combustibility, this is how fast the flame spreads in this. And the smoke and its toxicity. So how much smoke it is developing, whether the smoke is toxic or not, how fast the flame is spreading, whether it is self-extinguishing. You light a fire, you fire the insulation, and if you stop the fire, the insulation should not promote the fire. It should not burn itself down. So if the self-extinguishing property is there, that is a desirable property in the insulation. So even if one section of the insulation catches fire, it should not promote, it should not propagate, it should not go ahead, and it should not burn down the whole structure. So it is very important to have a self-extinguishing property and the low flame spread index. So today, these are the normal insulation material. What we were using is glass wool. Similarly, you have the mineral wools. Mineral wool is a very generic word. So glass wool and rock wool both are a part of that. So you have the ceramic blankets. So usually for very high temperature applications like furnaces, we use ceramic blanket. Why? Because glass wool and mineral wool, they usually have binders. And these binders are volatile. So once the temperature goes to 600, 700 plus, these binders will evaporate. So this material will become loose. So glass wool, mineral wool blankets, so they will actually lose their strength once you heat them up too large, because this binders will be volatile and they will. So ceramic wool blankets, they are usually used in the furnaces. You see it is a white color blanket. So they are usually white in color. And you can find, if you open the door of the furnace, like if you have a muffle furnace in your lab, if you open the door, you will see that there is a ceramic blanket inside. So this can very easily go up to 1000 plus temperatures. And then you have on the cold side, we usually go for polyurethane foams, puff, PIR. So these are some of the insulation material which are very widely used in the low temperature. You can also use glass wool as such, though on the closed cell structure, the puff and PIR are very popularly used. So these are all having conductivity in the range of 0.02 watt per meter Kelvin. So the PI foams, they are usually having 0.02. So now in the latest materials which has been added in the industry is called aerogels. So aerogels and microporous insulation. So these work in the range of 0.012. So usually these work in the range of the conductivity of the what should you say, air. Okay. So if you want to go below the thermal conductivity of air, people have gone for aerogels. So this is basically, aerogels are the nanomaterials. And how they work, I'll just give you some idea about it, though it's a very vast topic, but still I'll give you some idea how you can go below the conductivity of air. And then you can also form what is known as the vacuum insulation panels. So if you create structures, and in this structure you evacuate them, and then also try to reduce the radiation by using the highly reflected materials, and then you fill up with the microporous insulation here. In that case, effective conductivity goes. So this is the range you can generate. So this is called the vacuum insulation panels. But these panels are something which are rigid, so they are very costly. Only thing is you cannot cut them. You can't cut. So these are usually available in a blanket. So blankets you can very easily put wrap around. But vacuum insulation panels are, kind of, you have to build it. Like if a window structure is there, then it has to be built like that. And if there is a puncture, then what will happen? If there is a puncture, vacuum will be broken. So your vacuum insulation panel will not work. So this is the disadvantage of the vacuum insulation panel. So you are very much dependent on the kind of structures. So right now they are trying to work it out. Say for example, instead of having a single panel, if you have something like a modular, so what you can build up is a structure, and so if you want to cut it, then even if you cut it here, then this structure remains intact. So you can cut it also, only some part will be lost, but the entire structure will not be. So this is what they are calling as vacuum insulation materials. So instead of panels, whole single panel, you can have small, you can say structures within, and these structures, what you call as a vacuum insulation material. So you can cut them, but need not to have the breakage of the whole panel if you cut it partially. Okay. So this is what I was just telling you. The pyrogel. So this is pyrogel is a typical name which is given to that. So this pyrogel is actually an aerogel. So pyrogel is the trade name. So this is pyrogel. It is an aerogel blanket, and as you can see, this is the conductivity. Okay. So this is what is the ceramic fiber blanket. And this is the mineral fiber which you usually use, like your glass wool and all, rock wool. So this is your mineral wool. And this is your aerogel. This is what is microporous insulation. So microtherm is a trade name, and it's actually a microporous insulation. So microporous insulation is also a kind of nanomaterial like aerogel, and that's what you do. So aerogel were first developed by a company called Aspen, and slowly other companies also get into. So Aspen was developing this mainly. They use it for the NASA applications, and later on this technology became more commercially applicable. So Aspen's one of the you can say spin-off labs were developing this for the NASA applications. But nowadays many companies are making aerogels, and it is commonly available for commercial applications, including you can use it, in the jackets. See, its conductivity. The good part is its conductivity is very low. So you are working here. See, as compared to your conventional wool, which is having a conductivity of like this here. Suppose you are working in the temperature range of like this 100 or 50 degree or so. So if you see here at 50 degree, its conductivity is here. Whereas if you see the conventional mineral wool, it is here. So it is almost, you can say, half or in that range of this. So if you require a thick layer of mineral wool, with the aerogel, you can work with a smaller layer. So with a very small wall thickness, you can work. So you can use it in the shoes. Suppose you are working for mountaineering shoes. Okay. So there the sole of the shoe. So if your shoe is there, and if you put a small layer of aerogel here, so from the below, whatever cold is coming will be insulated. Likewise, in your jackets. So if you put a very small layer of aerogel, that will work wonders, and it will be light in weight, and it will not be very bulky. At the same time, it will be very effective. So this is what is the applications nowadays coming up. So aerogels basically they work on the principle of nanotechnology. I'll just give you some brief idea, though we'll not go into the more details because of the constraints available with this session. But as you know, this is how the structure of the nanotechnology is, that you have the nano, which you call as 1 nanometer. So it is somewhere here. The width of your DNA is like 1 nanometers. You have nanotubes, nanowires, and so forth. So when you talk of your blood cells, they are typically 1 microns. So, and likewise your human is like 1 meter, and in this dimension you can call as a human structure, whereas you can say the nanowires and the DNA, they are in the range of nanometers. So we all know that in this range you have what is known as the particle transport. So you work what is known as phonons. Okay, so at this structure the rules of physics, they change, and you can consider the energy which has been transferred is also through the phonons. And here you can believe that the lattice structure, the vibrations are something like, you can view it like a particle, and it's also like a wave. So the particle like behavior in what you call as phonons, and the vibration is continuously happening all along the lattice structure. And so phonon is actually a quantum mechanical description of an elementary vibration motion in which the lattice of the atoms or molecules are uniformly oscillating at a single frequency, like it is shown here. Okay, so you can see that in the case of the thin film, if you are using, then there will be a mean free path. So like in this case, the mean free path will be small. So in this case, it will be larger as compared to the length. Okay, so this length is very small as compared to the length here. So here, this is what is the effects of nanoscale come into picture, and the lambda of the mean free path divided by the dimension L is what is known as the Knudsen number. Okay, so if you are having a large value of Knudsen number, it means you are potentially working in the nano or micro scale effects. So here the physical boundaries, they change in that structure. And if you see the thermokinetic theory, it suggests that the thermal conductivity expression is actually given by this, where this is the lambda mean free path. So if you can manage this lambda of the mean free path of the phonon, then you can lower down the thermal conductivity. So this is what is used in the nanotechnology, and this is what you are doing when you are creating the aerogel or the microporous insulation. So you are basically playing with this, and once you reduce this, your conductivity also reduces. So if you want to control if you want to increase K, then you should increase this lambda. So the mean free path of the energy carrier, that is how you can control the thermal conductivity, and this is what aerogels do. Otherwise, the upper limit, or you say the lowermost limit, is constrained by the mean free path of the air molecules. But you can go into that, and you can create it by using what is known as the micro or nanoscale effects. So this is what you are controlling, and this is the typical characteristic of the pore size. So as you see, if you are using a 10 mm pore, so these are the various gases. Okay, so what you see with the black is the air. So as your pore size, so this is the pore in which you have trapped the air. So if you reduce the pore size, if you reduce it from this, right now in this you will have a different value of the mean free path. But now if you have reduced it, so your mean free path also reduces. And as it reduces, so as your characteristic pore diameter is reducing on this side, you see your thermal conductivity is dropping. So that is how, by creating the microporous panels or insulation, you can lower down the thermal conductivity. So you can, if you are using in the same micropore instead of air, if you are using a xenon, so this is the xenon. You see, for the same kind of pore, the xenon will create a much lower thermal conductivity. So this is like 0.005, or you can say 4 milliwatts, whereas for air it is around like 26. So for the same pore, xenon also creates a much lower. So almost 5 times lower as compared to air. So that is why air, if you replace air with some other gas like argon, krypton, for the same pore, the thermal conductivity will be much lower. So this is what aerogels and other insulation material are playing with, and this is how they create it. So these are some of the, you can say, the latest type of techniques people are using. So again, microporous insulation, I just told you about it. So this is how the insulation look like. Okay, so this is the kind of a blanket, and in between the two blanket, you have the silica agglomerates of particles, and they will be typically from 5 to 25 nanometers in size. So thousands of times smaller in diameter than the human hair. So what they do, they use the fabric like this, what you see here. So this is this fabric, and in this you have all this 5 to 25 nanometers size silica particles in which you have trapped the air or the gases. So this is what is known as the microporous insulation. Of course, the techniques required are very specialized. They are not available easily, and that is why this is costly. So you can use up to temperature of around 1000 degree, and they are very flexible. So you can create it like this. Aerogels we already defined. So aerogels, I'll just aerogel you can use on both the sides. Cryogel is used for low temperature application. So from minus 273 to 90 degree you can use it. So this is a cryogel, and this is pyrogel. Pyrogel is the again aerogel. Both are aerogel. Pyrogel used for high temperature. So minus 40 to 650. This is a pyrogel, and this is a cryogel. So low temperature. This is high temperature. So as the temperature will be low, you would not like the water to get into. So this kind of you can say a vapor barrier are used, especially in low temperature they are required. So they are put here. Though here you don't see it, it's not required here. Okay. So it's a very good insulation, and it is all flexible. So this is how the characteristics are. So your pyrogel is here, as you can see, and this is what is the conventional mineral wool blanket which you are using is going to be. So as compared to your pyrogel, you can see how the characteristic of the insulation is. So if you are requiring this much thickness of mineral wool, you can work with this much thickness of the pyrogel. So there is a lot of reduction in the outer diameter of the pipe. Especially in pipe, it is going to be very, very effective because your outer area of the surface will be reduced, because from there only you are losing heat. So even though wall temperatures are same, but the area of the outer cross section is going to be lower when you are using pyrogel as compared to mineral wool. So this is how you can also use it for in buildings, and now they also make transparent. So this is these are the translucent aerogel insulation. So the entire wall is like this. So light is allowing to come in, and heat is not allowed. So you see, so these are all walls. So what you see here, so all these walls, they are translucent type of aerogel. So lighting is very effective, and heat is insulated inside. So you are using the translucent type of aerogel. Vacuum insulation panel I just talked about. So you have the silica core as the opacifier, and you have evacuated it. So this entire thing is evacuated. Okay. So if you again you have to put some kind of porous element because it is evacuated. If you just keep it flat like this without filling something like a core material like silica core, it will collapse. So you need to give strength also. So and vacuum you require to properly weld the seams. So this is what is the range of conductivity. You see, you are able to get in the range of 0.004 watts per meter Kelvin. So almost you can say 10 to more than 10 times lower than the lowermost effect which you can get from other insulations. So vacuum insulating panels are, though it is costly. So I will just, I mentioned this construction, so I'll just skip this part. So this also I explained to you how the pore diameter is a function, and as the pore diameter reduces, your conductivity also reduces. So this is the fumed silica aerogel, where your gas pressure and also the pore diameter. There are two things which are important. So as you create the vacuum and also as you are creating the lower pore diameters, your conductivities are reducing. Water is something you don't want. You now know why. Promotes corrosion, increases energy loss, and it will also reduce the thermal efficiency. So you don't want water to get into it. Okay. So thermal efficiency usually reduces drastically. Why it will reduce? Because the ice, water in cold insulation, ultimately what it will form is ice. This is the conductivity of ice at 0 degree. So it is approximately 100 times greater than that of the. So when you are talking of air or the gases, it is 0.026. When you talk of water, it is around 0.6. And in cold insulation, water will again become ice, because on the other side you have a very cold wall. So this will lead to around 2 watts per meter Kelvin. So from 0.02 to 2, it is almost 100 times. So this is where you have to be assured that water is not getting into the system. And if the water gets into, the conductivity increases, and when conductivity increases, your you can say the walls will start conducting heat. If it is a cold insulation, you require higher refrigeration load. If it is a ambient kind of condition, then you require to have a larger air conditioning load. So this is where you don't actually require corrosion under insulation. I already talked. Again, water will promote that, and alkali and other things will also promote. So hot insulation properties, usually the objective of the hot insulation, we talked about three things: energy conservation, then process temperature control, and the personal protection. So, and here water entering is not important, because even if water enters, because it is a high temperature, so it can take care, because the water will evaporate eventually. But in the case of the cold insulation, very important thing is this. The other thing you have to take care is in hot insulation is the leachable chloride. So this will actually cause the corrosion under insulation. So this is a very important part you have to ensure. And the other thing is the mineral wool. So mineral wool has usually a resin as a binder, and usually this is a volatile material. And as the temperature goes more than 250 degree, these volatile binders will evaporate, and the whole wool will become fluffy. So there is a way how they will. I'll just tell you briefly. So this is how you work out the effective insulation thickness. So if you increase the layer of insulation, then definitely the cost of the whole thing will go up. Of course, your energy loss also reduces as the increase is there. But eventually you have to see how much cost the heat losses are going to bear to you. So, and you have to find out this break even point, wherein for this particular thickness, you will see that you get the lowermost overall cost. So one is the cost of the insulation system. As you put more insulation, cost increases. But as the cost is increasing, the heat losses also reduce. So these two graphs go opposite, and this is the mean graph. So at this thickness, if you put the insulation, that particular insulation, you will get the lowermost cost benefit. So this is how the economic thickness of the insulation is worked out. Then these are some of the additional things. We'll skip this part. Cold insulation. You just got the idea about cold insulation. In cryogenic systems, you will use it. Here, your objective is basically to conserve the refrigeration. and also the boil-off rates and the temperature control of the processes, also to prevent the surface condensation and ice formation, and of course the personal protection from the cold burn. So here, what is most important is that the water should not get inside your insulation, because if the water gets inside the insulation, it will definitely damage. And how it will do that we already discussed. So you have to ensure that the at no place the problem of the water seepage is there. Also, the piping and the equipments in the cold service will undergo some contraction, and if some part may be under the ambient, so how the expansion, relative expansion takes place and contraction take place, that is very important. So the cold insulation system, you usually also require what is known as a vapor barrier. So this is, you can say, one of the very important part of the cold insulation. So as I just showed you on this here. So this is the vapor barrier you have put here. So this is a cold insulation cryogel. So you don't want moisture to get into, so you have used this as the vapor barrier. Though in hot insulation it is not there. So CUI, just I explained to you, this is how the corrosion under insulation happens. Okay. Fire protection, very important. I'll just we'll discuss it briefly in the case of some of the applications, how fireproofing and how fire protection is important. So as I was telling you that the insulations, what you can do is you can put aerogels are very costly. So that is the only disadvantage with them. So if you want that the material should have a long life and also it should not have corrosion under insulation, what you can do is the pipe which is immediately in touch, you can put a small layer of aerogel here. So suppose you, for the same application, if you put 20 pyrogel, it is going to give you the same surface temperature. So for as compared to 0.8 pyrogel, the calcium silicate required will be of 3 inches and an expanded perlite will be of 3.5 inches. So you see your outer diameter is increasing, so your outer area is increasing, so your heat losses are also going to increase. Those temperature here is same as the temperature here. So this is the advantage, but the aerogels are expensive. So what you can actually do in this case is also in hot insulation also same thing. When the high temperature happens, suppose a pipe having 550 degrees Celsius temperature, if you put mineral wool, all the mineral wool will get the its binding material or the its volatile binder is there. So this binder actually keeps the blanket in proper shape. So this zone is known as burnout zone because in this volatile material will evaporate. So this over a period of time, this whole thing will lose its strength. So though you have put the mineral wool blanket here, but over a period of time, this will become loose because of the high temperature. So here, instead of using this, you can use an aerogel. So aerogel, if you use, there are two advantages. Aerogel does not have any binder, so it will be intact. And the second thing aerogel will do is it will, for the same layer which is going to create here, aerogel required will be much lower. So it will outer diameter, then afterwards you can put a mineral wool again. So in the outside the burnout zone, you have mineral wool, so you are working on the cost effectiveness. And at this level where you have maximum chances of burnout of the binder, you are putting aerogel. So overall outer area reduces and your material is safe for a long time. So this is how you can optimize, and you don't want to put the whole material of aerogel because that will be more costly. So you put mineral wool and inner layer you can put of aerogel. So that is how people optimize on that. So this is something we can conclude today's session. And I'll have some 2 or 3 small videos which I will share with you after the conclusion. So one thing is that thermal insulation materials are the key tool in designing and constructing energy efficient, energy thrifty systems. The vacuum insulation panel, aerogels and microporous insulation, they are as on date the most efficient options available. Aerogels have the potential to exhibit low corrosion under insulation, and also they are very sturdy. So this is something which we can conclude from this session, though they are expensive. Aerogels are expensive, but how you can optimize, just I told you. So let us see some of the videos before we close, and I'll come back to some questions, quick questions afterwards. So the first video which I want to play is about aerogel. What exactly is aerogel?
From insulating astronauts in space to crude oil 10,000 feet below sea
Video is not playing.
Aspen aerogel
Sorry?
is the
No, video is not shown, sir.
Video is not visible.
Achha, it's not visible. Okay. So
Sir, you have to stop sharing this presentation and then share that video again.
okay. Okay, I got it. Has it stopped?
Yes, sir. The presentation is
Yes,
stopped.
sir.
Okay. Just a minute. So do I need to? Is it showing now? Is it visible?
Yes, sir. Yes, sir.
Okay.
From insulating astronauts in space to crude oil 10,000 feet below sea level. Aspen Aerogels is the recognized leader in aerogel insulation and energy conservation. Aspen's leadership stems from its patented nanotechnology that converts the aerogel into a practical, flexible blanket. These blankets are quite simply the best insulation available in the world today, offering 2 to 8 times better performance than any other material. To demonstrate the amazing insulation effectiveness of Aspen aerogels, let's look at the temperature change between this oxyacetylene torch with a flame temperature of 1,000 degrees Celsius and the other side of this 6 millimeter Aspen aerogels blanket, just 100 degrees Celsius. The insulating performance is just as phenomenal at low temperatures. So let's see the temperature change between this block of dry ice at minus 78.5 degrees Celsius and the same 6 millimeter Aspen aerogels blanket, room temperature 22 degrees Celsius. Aspen is already conserving energy and improving performance in oil and gas pipelines, natural gas ships and storage facilities, industrial and refinery operations, as well as defense and aerospace, appliances and apparel. Today, Aspen scientists are creating more innovations that will result in new levels of energy efficiency and value for building and automotive and acoustical applications. Nanotechnology at work.
Okay, so this was about the aerogel. Now, many times we do not understand exactly how crucial in hydrocarbon and other facilities the effect of insulations will be. So let us have one accident was happened in a refinery. Just have a look at this. Temperature management is very crucial. Again, in a building, suppose you are using an insulation, how the building will catch fire. This is a simple video. It is actually promoted by NIST. So if you are using an insulation or if you are using a material, and how actually the buildings will catch fire, and something to just sensitize on that. This is a typical living room, and you are using say a foam. Foams are usually used in houses. People also use it like in sofa. For example, a foam is burning here. How the fire actually spreads in a house. This is just an example. So when you're using an insulation like polyurethane foams and other things in a building, you have to be very cautious about the type of chemicals which have gone into its construction. So this is just, you see, after the fire started, how quickly the fire spreads. So it is just 30 seconds have happened.
Sir, have you shared the video because it is not yet visible?
Okay, it's not visible.
No, sir.
Okay, just again it looks like
You have not. Yes, you have not shared it.
Okay, just a minute. Sorry, then I think you'll have to. Every time I have to share it. Okay.
Yes, sir. You have to do it again.
You saw the previous one?
Yes, sir.
That was visible, right?
That was visible.
Okay. Now it has come.
Yes, sir.
Okay, so this is a fire in a living room. NIST actually just to make people aware of how fast the fire actually propagates. So it is just started when 5 seconds have happened. This is around 45 seconds. So this is a scenario in about 1 minute. As you can see, smoke is also a very important parameter in fire. So what kind of smoke is generated? So it is almost like 1.5. So 2 minutes almost approaching. So you see how much time you have. So this is in 2 minutes, this is a scenario. So if you are using any insulation in the home for any kind of application like walls and all, you have to be very sure of its fire resistance. So this is in hardly 2 minutes, you see. So this is less than 3 minutes. So this is the situation in 3 minutes, you see. So practically you don't have much time in a situation like this. So this is 3 minutes and 20 seconds. See, the entire room is in fire. And finally, the last video which I want to play is stop sharing. So here, okay. So there was actually a in US. There is Rhodes Island, and there was a nightclub there. It's called Station Nightclub in 2003, February 2003. There was a rock band was playing, and in that building they had used on the rooftop. They were using, actually it's a nightclub, so they were using insulation called also for acoustic plus the thermal application. So the foam which was used here in the building, and it is not uncommon. Foams are very widely used in buildings for air conditioning, reduction in the heat load and other things, and also for acoustic purposes. So there was a fire, and more than 50 people died because of the suddenly, as you know, in a room, if there is a fire catching up, and how fire catches happened is they were using actually pyrotechnics. Pyrotechnics means they're using some crackers, because in rock bands it is very common, and that went up to the ceiling, and the ceiling caught fire, and then the whole room was in fire, and the exits were very less. More number of people were there, so more than 50 people died in that mishap. So how the actually fire may have happened? So the NIST recreated that scene, and that's just to. So you can see this. Okay, is the video visible? Hello.
Yes, sir.
Okay, so now here,
visible,
yeah, here at this end, so the fire catches up because of the pyrotechnics, and now see the entire wall is made up of foam. So you see it is just 20 seconds before people actually realize the smoke is also coming, you see, and once the smoke, so within 20 seconds, the entire 30 seconds, you see. So this foam also makes the visibility very poor. So in the case of thermal insulation, especially applying it for buildings, you have to be very cautious of the fire properties. Usually your rock wool and mineral wool are safe as far as the fire is concerned, but polyurethane foams, they are very susceptible to fire. So you have to see that you have used the fire retardant chemicals in the construction of the foam material. So you see in less than 1 minute, this is the scenario.
No.
So this is 1 minute and 20 seconds.
Sir. Sir, hello, sir.
So this is 1.5 minutes. See, this is the whole thing gone blank. So this is what may have happened on that day. Okay. So here I will stop this presentation also, and maybe we can come back to our PPT. Okay, fine. Any questions you have? So if you have any questions, I'll be happy to take.
Sir.
Yes.
Sir, thermal conductivity is directly proportional to the mean free path, right?
Right.
Right. So we can say that. So we can say that the mean free path is also affected by the temperature.
Actually, this will be definitely affected. In fact, with the temperature, your what should you say? The rate of the collisions will also increase. So indirectly, in a microstructure, your rate of vibrations will also increase. So as you can see that for all the materials, the thermal conductivity increases with temperature. So you find that with the temperature, thermal conductivity is increasing. So if you see a plot like this, so with the temperature, thermal conductivity for all the material, including the aerogels, pyrogels, all the cases, the thermal conductivity increases with temperature.
Oh.
Yeah. So we find that in most of the materials, like, yeah, hello.
This is Karthikeyan from Kadalur, sir.
Yeah, yes, sir.
So how to calculate the PU of insulation thickness required to cover up a flat plate solar collector, sir? Normally, we have arrived at the value from the thermal resistance given by the manufacturer. So what is the technique that we need to follow to arrive at the exact thickness requirement, sir?
You should set the temperature of the surface which you want to achieve. So if you set that temperature of the surface which you want to achieve, you can calculate at what thickness you will be required to have.
So is there any relationship available for that, sir? Any formulas or something like that?
You can do it from basic calculations of heat transfer, just fundamental calculations. So
okay, sir.
You can,
and,
yeah.
Yeah, when we design such green energy systems by involving PU foam as an insulation material, people are objecting by saying that PU foams are not eco-friendly. So in such case, what is the most popular eco-friendly insulation material available with the least thermal conductivity, sir?
Actually, if you see the organic materials, organic materials, you like even your newspaper, paper is a very, paper has cellulose and those kind of things. So coconut fibers. So if you talk of green materials, then these are the materials, but only problem with them will be their conductivity will not be as low as the material of the foam. So if you see the foam conductivity, they will be typically in the range of like if you talk of puff. So
yeah, 0.024.
Yeah, 0.02 to 0.03. So in that range you will get. Whereas if you take the material like wool or say paper or say coconut fibers, so these kind of things will have say from 0.1 to 0.2 and in that range. So you get the order difference here. But though these are eco-friendly, so they will not have a problem. But this of course is a kind of a synthetic material, is a kind of a, you can say a plastic only in a way.
So that means there are no eco-friendly materials available to match the thermal conductivity levels of PEF. Am I right, sir?
Yes, only thing is if you can use something like where air pockets are there, like if you can, like, ultimately how is the puff doing? It's a wall. This wall is made up of, as I told you, this wall is made of puff material. It's a foam, polyurethane foam, and inside it you have filled some kind of refrigerant or some kind of air pocket is there. So refrigerants usually they use because its conductivity is even lower than that of air. And that is how it is able to get the air's conductivity of around 0.02. So if some material can be there where you can have this kind of a pocket created, it will be very good insulator. But usually in nature you don't find this and you cannot create such structures so well. But air as such is the very you can say good insulator. So if you can create say a small layer of air in between. So if you have a wall and if you keep a very thin layer of air in between, so even this will work like a resistive material. And over that you can put your insulation. So you are creating one more path of resistance. So one path is this, one is additional is this. So this is delta x upon Ka is the resistance given by this. This is also delta x upon Ka. So this K is related to the air's conductivity. So, but if you keep this too thick, then air will start also convecting. So you don't have to start convection. You have to only induce the conduction. So the air's conductivity you have to use. So once, if this layer is hot and this upper layer is cold, then air will start moving in. If it is reversed, then convection will not happen. Then only conduction will happen. So we can use air pockets. So that is air is freely available. So that is something you can use.
I understand. But in market there are different densities of foams available. So right. What is the bearing of such density on the thermal conductivity values or the thickness?
Again, the thermal conductivity of foams, again, as I told you, it will also depend on the open and closed cells. So this is something which is very important.
Whether we need to go for a much lower density or for a relatively higher density, sir?
Here the high density foams are there, but as I told you, see if you remember this diagram, So if you see here, if you make this smaller, so how your structure is. So here, if you make this very small, so your density, if you go for low density foams, then definitely your this structure is bigger as compared to the high density. So yeah, smaller structure, but along with that also the open and closed cell. So if you are, these paths are open, so what will happen? Air will also be moving from one side to another. So this will be conducting the heat. So what is the open and closed cell? That is also one of the important factor along with the density. Okay.
Thank you, sir. Thank you, sir.
Yeah, thank you. Yeah.
So, I am Himanshu from Mehsana.
Right.
You have discussed about the hot insulation material and cold insulation material.
Right.
And I have mostly seen that in application of cold insulation material, there is use of puff and thermocol EPS. That is.
Right.
So we can replace that material with glass wool. Is it possible?
Yeah, glass wool, you can replace it. Only problem, as I told you, happens is of the water penetration. So in the cold insulation, of course, glass wool can also be replaced. People sometimes use it, but only problem which will happen with the glass wool is the penetration of moisture. Suppose you have some hole, ultimately puff does not have much water, going into it unless the cells are open, as I was just telling. But blanket is like fibers, and in between fibers water can enter. But the structure of the puff, so just I was just showing you this. This is the difference. Your glass wool blanket is like this. This is layers. These are layers, and in between these layers, water can enter. But here, puff is having a structure like this. So if you are, unless your cells are kind of open, water will not easily get into it. So you have to take care of that. And once water gets into cold insulation, this water will enter it and it will not be able to come out. In hot insulation, water will evaporate from the hole from where it has entered. But in cold insulation, water will become freeze to ice. So air was having conductivity of 0.02, water was having a conductivity of say 0.6, and ice has a conductivity of 2. This water will convert to ice because it is a cold side also. So ice will also expand. It will damage the insulation. At the same time, its conduction is from 0.02 to 2 means 100, factor of 100 you are increasing. So this is the issue. But
okay,
that is why.
Yes, sir.
Yeah. Yes, tell.
And what will happen when you will use puff in the application of hot insulation, like in furnace, high temperature furnaces?
This will melt. This will melt. Usually, most of the puffs are usually you will go only up to 100 or so. If you use it in high temperature, this is plastic only. This will melt.
Okay. Yes,
Yeah.
got it. Thank you very much.
Okay, thank you. Okay,
So I think there are no more questions. So on behalf of this entire team, I am very much thankful to Lakera sir for this fruitful session, and thank you for your session, sir.
yeah, I also thank you, Professor Ragesh and Dr. N.M. Bhatt Sahab, and all the participants. You have been a great audience, and I thank you for also being patiently listening to the session for the last 1.5 hours. And I hope I could throw some light on the insulation. Still, if you have any questions, further questions, you can write to a mail to me. My email ID I'll be sharing with the first slide of my PPT. And once again, I think I'll share my first slide so that you can. Is it visible? Anyway, you'll be sharing the presentations, right, with the participants. Yes, sir.
Yes, sir.
Okay.
Yes, sir. That would be
Okay,
shared.
so my email ID will be there, and you are welcome to ask any questions if you have at the end of the program as well, and in future as well. So thank you very much, and hope you have a great learning STDP this one, and wish you all the best. Thank you very much.
Thank you. Thank you very much.
Thank
Thank
you.
you, sir.
Thank you.
Thank you, sir.
Thank you. Thank you very much.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
All the participants are informed that we'll meet tomorrow in the first session at sharp at 11 a.m. So everyone is requested to join before 10 minutes. So that's all for today's session. I hope everybody is enjoyed, and we will continue